try to keep it as popular as possible. And I will not get into too much of scientific details, but however, if anybody has any question, you can always ask me. I will be happy to answer them. So now I will share my screen. So is the presentation visible? Hello?
Yes, sir. Yes, sir.
Yeah, okay. Thank you very much. Okay. See, when Dr. Jitendra Patnaik called me and asked me to speak about something, so I was wondering what to actually discuss, because this year's Earth Day is being celebrated, and it has a slogan, so which is different from what I will be speaking. Nonetheless, I believe every reservoir of the Earth, every part of the Earth, in a way, uh, should be nurtured. So we as human beings are part of this system. Should always understand the processes and try to see that we do not hamper the nature that much, so that it affects us in the future. So anyway, having said that, I will actually discuss something which I am familiar with, and I'll because he said we should talk about volcanoes a little bit. So I thought I'll share my experience, our team's work in the volcanoes we have studied in the Indian subcontinent. So I was wondering which part of the volcanic story I should tell. So then I realized that people may be interested in to know that volcanoes, the way we know it, our scientists, our geologists know it, our common people for the say, is the type of volcano on the right. Sorry, on the left, you see. I don't know, it will be right on your screen probably. So it's a picture of our only volcano in this continent. I mean, in Indian territory. It's called Barren Island. It's an active volcano. So I'm talking about active volcanoes. And then there is a volcano look-alike. It's not a volcano. This picture that you see, it's not really a volcano. However, it has a name called mud volcano. So the volcano word is there because it has a similarity in features, but in a much miniaturized scale. If a real volcano, which is a high temperature lava emitting volcano, could be kilometers in high and kilometers wide, these volcanoes or the mud volcanoes are a miniaturized version. They will be most of the time they will be in several feet, or at the best it will go to several meters. So you can see the difference in the scale. So I would like to compare these two and tell you a story through our journey, and what kind of information you will gather if you study these two different type of volcanoes. One is a real volcano, or we call it high temperature volcano, and the other one are the mud volcanoes, which emits mud, whereas the other one emits molten rocks as lava. So these both are in the Indian territory and both are in Andamans. All right. So what are volcanoes? I mean, for a common person, volcanoes are basically openings on the planet's surface where molten rock, ash, and gases escape from deep interior. So you must have seen many volcanic pictures. I have a couple of pictures here. One is in Aleutian Island and the other one in Hawaii. So these are, as you can say, either you get this ash or lava, and they are extracted very deep from the Earth's interior, as deep as sometimes going to probably 100 kilometers or so. So from that depth, the molten rocks are extracted to the surface of the Earth. So these are the volcanoes in the real world, or we call it high temperature volcanoes, because the temperature of lava that gets emitted will be somewhere around 1100 to 1300 degrees Celsius. But there are low temperature lavas as well, but not as low as the mud, which will be like a normal temperature of 25 degrees Celsius. So this is a sketch. It's a cartoon just to show you anatomy of a volcano. Many volcanoes are many different types. This is not strictly a type of volcano one would expect. However, this kind of volcanoes are prevalent in the Indian territory, in the sense in the Andamans. These are called stratovolcanoes. So what you will see piles of rock and ash making up the actual cone of the volcano, and there will be a magma chamber deep within the crust, sometimes going to several 30, 40 kilometers, maybe in the crust mantle boundary or below it, where the magma will get stored, and whenever it has sufficient pressure, it will get emitted, or at times it will be pulverized to give you ash and all that, and there will be a lot of fluid emissions. So a typical volcano along a subduction zone or along the boundary between convergent boundaries would look like something like this. So where do we find these volcanoes? So most of the volcanoes are actually uh, people who understand plate tectonics. I'm pretty sure geologists in this audience would know about it. So most of the volcanoes are actually confined to a certain plate boundary, and we call it ring of fire. As you can see, these are all red triangles at the volcanoes. So they mostly occupy a boundary between different tectonic plates. However, there are volcanoes which also occur within the plates. So there are many different type of origin. That's why they are located. For example, Hawaii is within plate volcanoes, and it's all these are active volcanoes, present day volcanoes, and Hawaiian volcanoes are related to what we call hotspot volcanism, whereas all other volcanoes what you see are primarily related to plate convergent boundary. That means where one plate goes down another plate, whether it is oceanic or oceanic continent. So these are the places where you get volcanoes, and also these are the places where you get maximum number of earthquakes. So these are the real volcanoes. So we call it ring of fire. So why should one study volcanoes? I'm pretty sure many of you already know. First of all, I like this one that there are spectacular landforms. So people who have seen volcanoes, they would know that how beautiful they are in the real sense. And this is Kilimanjaro in Africa. So if you go to South America or other places where very large volcanoes are there, even Hawaii, so they are huge, and they are so spectacular that you would actually like to know how did they form, and how long did it take it to form. So same way, we study volcanoes because they also carry a lot of minerals and deposit them. So this is an example of sulfur deposit. So but there are many different kind of metal to and non-metal deposits that are created by these high temperature volcanoes, which are of course beneficial for us. So therefore we should study volcanoes to know these mineralization processes. Same way, volcanoes can also cause hazard to life and property. If cities are near the volcanoes, there is always a threat when the volcano becomes active. It might, and in many cases, it has in the past and it will be in the future. It will actually kill people or kill life or destroy properties, etc. So this is one example from Pompeii, where Mount Vesuvius actually destroyed the entire city. That happened around 79 AD. So that is why one should also monitor and study active volcanoes. And the most part, geologists are interested in studying volcanic material which are erupted onto the surface. And in the planet's history or Earth's history, we have many such activities which are taken place over last 4.4 billion years, whatever records we have. So why should we study them? Because they actually the record keepers of the planetary evolution. How the Earth as a planet has evolved, particularly the interior of the planet has evolved, would only be deciphered if we study these rocks, their geochemical properties, and try to understand how the interior has behaved through time. So, therefore, it is necessary as a researcher or anybody who is interested to understand planetary evolution should study this material which are erupted by volcanoes. So, we call it volcanic rocks. So yes, as I just told you, the apart from all that hazards and beautifulness and mineralization, etc., they serve some kind of window to the Earth's mantle. So if you study them, these are Meadowsonic ridges on the right, if you see. So the Meadowsonic ridges are the longest volcanic chains on the Earth's surface. They are located under the sea, on the sea bottom. So they carry a lot of information that otherwise would not be available to us if you had studied only rocks on the continents. So they basically serve windows to the Earth's mantle, and thereby it will shed light on the planetary evolution. Now let's go back to the other type of volcano. So this volcano is a misnomer. They should not have been called volcanoes. Nonetheless, they have been called. So here we are. We have to deal with it. So what is that? Why they have been called volcano? If you look at it, these are mud volcanoes. This looks exactly the way lava would flow. These are mud flows. So what is mud? Basically, you have clay minerals, and they have a lot of water, and they also carry a lot of clasts which are picked up on the way when they're erupted. They also form some kind of mound, but as I told you, in a much smaller scale, and they look like lava, but the temperature of this mud is very low. It sometimes it could be lower than the atmospheric or ambient temperature. It could be 20 25 degrees Celsius. So what is so interesting about this, that not only they carry clay minerals and water, they also carry hydrocarbon gases. So you'll see this is a bubble actually where the gas is emitting. So most of the time these gases are methane, CH4, and many a times also higher forms of hydrocarbons do get emitted. So constantly it emits, and you also see a lot of organic matter gets emitted along this. Now, where do you find such volcanoes? Real volcanoes are found all along, let's say, convergent boundaries and sometimes intraplate. But these are mostly found along where you have high rates of sedimentation. So, by definition, mud volcanoes form as a result of emission of depressurized pore water. So, at a very deeper level, maybe more than 5 to 6 kilometers or even further down, where you have sediments piled up for a very long time, your clay minerals which are there, they get once you have compressed them to a very high degree of pressure, they will start releasing water. So this water, if there is some kind of tectonic movement or fractures, or there is another gases are pushing up from the hydrocarbons, or let's say decomposed organic matter, a lot of gas will try to escape. So then this water actually flows. When it flows, it carries the mud or the clay minerals along with it and gets evacuated or ejected through certain vents, thereby forming this volcano look-alike features, but at a much smaller scale. So where do we find these mud volcanoes? They are very common where you have high rates of sedimentation. For example, our Bay of Bengal, because we have very thick sediments. Same with Indus Delta, for example, or Ganga Brahmaputra Delta, where just in the seashore, beyond certain level where the deposition rate is very high, you will see these kind of features all along the boundary, and also you get them in convergent boundaries. So where the sedimentation rate is high, as well as there is a convergence of plate, so these sediments get compressed, and because of that, this mud tries to get out from the very deep interior of the sediment pile. So that will come as mud volcanoes. If you have fractures and all, it will ooze constantly out of it. So some pictures of mud volcanoes. So these are basically subsurface mud that gets extruded at the surface. So they are usually smaller features, but at times there can be as high as 200 meters, and they could be as long as several kilometers. Even then, it is much smaller compared to the real volcanoes. So they are not really confined like their real volcanoes into certain boundaries. Wherever there are high sedimentation rate, you will find them. But you do find them along convergent boundaries like this. For example, our Andaman subduction zone. So this is just a cartoon. If you take a cross section of a mud volcano, you will most of the time you will find there is a feeder channel through which this mud is extruded to the surface along with gas. So mud, water, gas, and fragments of the rocks from the surrounding through which it is passing, they get emitted or ejected. And if you have enough methane, sometimes they catch fire, so you will have a fire also burning. So you can imagine that at times when the eruptions are rates are very high and you have a fire, they may look like real volcanoes, but they are not real volcanoes because methane is there. It will catch fire very easily, and so it will look like as if some volcanic material is getting erupted, but it is actually the clay and water they get emitted. So yes, whatever I have told. So most of the time you will see them on top of sea floor or surface piercing shale diapirs. So diapirs where you basically, I don't have a picture, but shale diapirs you can imagine when it is mud basically that when it decompresses, it comes up and then you have these features. Okay. So why should we study them? Right, the real volcanoes, which give us information about the deep interior, these volcanoes give us information about very interesting things. It because most of the time they are related to hydrocarbon deposits. Because this methane that gets emitted from mud volcanoes actually come from deep interior of the subduction, sediment pile, where the decomposition of the organic matter is taking place. In other words, that is where the oil petroleum formation is going on. So that means if you study mud volcanoes, you may get some idea whether that particular petroleum which is getting generated is mature enough to be extracted or not. So it has an implication for petroleum deposits, and it is also related to seismic activities, particularly along convergent boundaries. Whenever there is some kind of earthquake, you will see more emission of gases. So sometimes people think if you monitor mud volcanoes, you can actually monitor the earthquakes, and some believe we may be able to predict earthquakes, but it is still a long shot. Nonetheless, this has been seen that whenever there is earthquake, you have more activity along mud volcanoes or of mud volcanoes along the convergent boundaries. And whenever they are located along convergent boundary, they actually provide a window to the four arc processes. So I'll come to this in Andaman subduction zone, for example, that we have a thick pile of sediments called accretionary prism, and below it, what's going on, how much of sediment is actually getting subducted along the decoloma, what kind of processes are happening. We don't have direct access to this. That means we don't understand what actually goes on along a subduction boundary. So mud volcanoes, they carry material from deep enough to give us some idea about the processes or reactions that's going on there. So if you study mud volcanoes and the material extruded or ejected by it, we may be able to have some idea about the processes along a subduction boundary. And then it has climatic implication because a lot of methane are emitted, and so if you calculate all the methane that comes out of volcanoes, mud volcanoes, all along the subduction boundary or elsewhere, you may be able to see that how much it actually contributes to the global emission of methane. So I know that the IPCC has included mud volcano emissions into their calculations because it forms a significant part of greenhouse gas emission, because methane itself is a greenhouse gas. So it is a natural emission. However, this constitute a significant portion of methane emission in nature. And geohazard, of course, muds can flow, and if you have civilization nearby and there is a eruption, it may actually mud flow can bury your houses, etc. So those kind of things are there. And if large scale methane emission is there, it can catch fire and it can burn forest and all that. So therefore one should study these volcanoes. So these are two different type of volcanoes. So let's see where do they form, these mud volcanoes and the real volcanoes. So real volcanoes, as I have told you, they are mostly confined to plate boundaries, and these are various kinds of volcanoes we know of. So I don't want to get into detail. So you have island arc volcanoes, then you have intraplate volcanoes or mid-oceanic ridges. So these are the real volcanoes. Okay, so these are the four different tectonic, or you say, boundaries where all these volcanoes form, or the four zones where these volcanoes form. So these are high temperature volcanoes. Whereas mud volcanoes are generally found like this. I was talking about mud diapir. So when there is a compression, lateral compression as well as vertical compression, a lot of pressure, so this mud extrudes because most of the sediment that carried into the deep sea will be rich in mud. That means clay minerals, because larger grains will be deposited close to the shore, the finer ones will get into the deep, and then for a very long time, if deposition goes on for several kilometers, then at some point there will be a fluid pressure will be enough to extrude or eject this material out of the pile. So that will cause eruption of mud volcanoes. So along accretionary prism, so this is a picture of a subduction zone. So along the accretionary prism also, you have fractures or even faults through which this material from the bottom of the pile will come up as mud volcanoes. So these small features you see, these are the mud volcanoes in a subduction zone environment, particularly along the accretionary prism. So this is called accretionary prism, where the sediments are deposited. So the real volcanoes will be on the island arc side, where the subduction goes in. And of course, I will not get into detail. The fluids generate melts, and those melts get high temperature melts will come up, and these are real volcanoes. These are mud volcanoes. So in a subduction boundary, the relationship is something like this. So why did I show you that? We'll go into the Andaman subduction zone, where both of these types of volcanoes are available for us to study. So this is a picture, Google Earth picture, where this is the region we are interested in, Andaman Nicobar Islands. And if you have a closer look, so this is the subduction boundary or the convergent boundary. So where Indian plate is subducting beneath Eurasian plate, but actually this is called Burma plate. It's a sliver of Eurasian. It's a smaller plate, microplate you can call it. So that's the trench. This is the trench, and that's the direction, which is a kind of oblique. So this Indian plate is subducting obliquely beneath Burma plate, around 4 to 5 centimeters per year, and that's the accretionary prism or wedge, where a lot of sedimentation is going on. So you have to imagine this Bay of Bengal is very thick sedimentation is there. So part of this sediment is actually also on this, and it is subducting as well as getting deposited. Not only that, a lot of sediments also come from Burma through Irrawaddy, Saluin, Sitang, all these big river systems. So if you have a subduction zone, as you may know, that we may have island arc. So here the island arc is only consists of very small volcanoes. There are only two of them subaerial, that means above the sea level. There are only two known volcanoes. One is called Barren Island, the other one is called Narcondam. So Narcondam is an extinct volcano, and Barren Island is the active volcano. That's the only active volcano in India. So that's the Mid-oceanic ridge, which is, we call it back arc, which is opening up. So it is splitting the Andaman Sea into two, or Andaman Sea floor into two. So that's the spreading ridge. So I won't get into all those. So based on geophysics and all that, we can imagine how it would be like that in the interior. So you have to imagine like this: the Indian plate is subducting beneath Burma plate, and here you have the Andaman Islands, which is an accretionary wedge or prism, and then you have a arc crust, and you have island here which is volcanic. That's the Barren Island, and then you have a back arc basin, which is the Mid-oceanic ridge in the Andaman Sea. We call it Andaman Ridge. So where Mid-oceanic marble-like melt is being produced, and here you have island arc lavas as volcanoes. So if you study this, you might understand what's going on here. Okay. And where are the mud volcanoes located? They are located here on the Andaman Islands. The real volcano is here. Anyway, I'll come to that again. So I'll take you through whatever we have studied. Of course, I will not be able to get into all the details. So I will give you a tour of all pictures, some of the pictures which I have taken, and try to make you interested in the volcano and what we can understand by studying this volcano. So this is a picture of Barren Island volcano. We can see some active emissions are taking place. These are basically ash emissions. This picture was taken in 2007. So, as you may know, this volcano was dormant for a very long time. So, this is a picture of volcano or a cartoon or you can say sketch taken in 1787 by British sailors. So, they drew a picture of Barren Island. Okay, so you can see they saw a very small cone inside and a caldera, and the volcano they thought looked like that. Then, for a very long time, nobody really studied it except for Geological Survey of India. And in 1990, as you may know, this volcano became active again. For a very long time, in between, of course, there are, this is, I have written here, the major eruptions have been reported around these times, 1987 to 1832. There have been eruptions, intermittent. Of course, there was no constant monitoring, so nobody would have known. But from 90 onwards, we have been, our GSI and many other people from India have been monitoring this. So in 91, the eruption happened again, and then it has been active since then. Of course, these major eruptions are listed here: 94, 95, 5, 6, 9, 10. So these are lava emissions. Whenever there is lava flow, so those have been recorded here. But most other times, you will have eruptions like this, where the ash cloud will be there. A lot of ash gets generated or ephemerals and all that. So some records are there with Coast Guard as well as GSI. 92 it looked like this, so that's on the island. And then 2003 you can see there is an opening on the caldera wall where lava is actually coming into the sea. This is an aerial picture in 2005 eruption. So you can see new lava flow is coming. And because you have a break in the caldera wall, this lava pours into the sea. So in that sense, the island is growing. And of course, this 2005. So how do you reach Barren Island? This is a simple, map. This is the Andaman Islands. Port Blair is here. Here is Port Blair. So from there you have to take a ship or a boat to Barren Island. So that's where Barren Island is located, roughly 153 kilometers or so. And once you reach, this is how it looks. So it has grown quite a bit because I myself have observed it intermittently, of course, from 2007 onwards. So every time we go, we find some changes here and there. But this was the last picture I took, so you can see it has grown quite a bit. Particularly, so the central part is called cinder cone, and that's the lava delta. So more lava is coming out, and of course the activity also kind of intermittent. It's not a continuous thing, but nonetheless, it is still in the active phase. So this is how you go. You go take a coast guard ship, get down on a small boat, and then land on some kind of opening beach or wherever, whatever you find safe enough. And I'll show a couple of videos if that is, I don't know what this is. Yeah. So this was in 2009. We saw some activity. So that's the lava flow falling into sea, and that's the emission you can see. Okay. So that was 2009. The very next year, again, when we went, we saw a little bit more activity. So that's the sound you heard. It's actual sound. Okay. So when you have large scale eruption of ash or lava, particularly lava, you will not have that kind of noise. But this kind of ash eruptions, ejection might be with a lot of loud noise. So that's the real noise you heard. And then at times you can see the cinders coming out. If you are lucky enough to arrive early in the morning, you may see this. So what you see, they are called cinders. Okay, you know what is a cinder in English word. So this cone is made up of those cinders, and at times you will also get lava coming out. They flow down the ridge. Sometimes they puncture the ridge and come out. So this kind of activity happen on the island. Uh, I mean, if you remain there, watch it, you may see all kinds of things. So what when we studied, we had lot to study because very little information was available. So obviously, if you go to a volcano, you want to study the volcanology of it. Particularly, different types of volcanoes are there. We type of lava flows and eruption style, etc. So a lot of field is required. But the problem is logistics. Since it is located far away, you have to take help of Coast Guard or Navy, so you have limited time to study. Nonetheless, we tried, and there is no water available, so making a camp is difficult, but people have tried. I have not personally tried. And then of course we need the historical data. uh, okay. So, and also we tried to date the volcano in the sense it date to lava flows and try to understand the frequency of lavas and frequency of eruptions, as well as the timing at which it came out of the sea. You have to remember this volcano is located in a sea where the depth of water is roughly 2 to 3 kilometers, and then the above we have roughly 300 or 40 or 50 meters. So when did this um, volcano breach the surface of the sea? So that means the bottommost lava flows need to be dated, which we did. And then if you want to know the frequency of eruptions, you have to study things which are in the sea. That means those ash you saw, they get erupted, get deposited in the sea. So you can take a core from the sea. I'll show you how you do it. And then you date the ash beds using carbon 14. That means ash beds will have foraminifera from the sea, which can be dated by carbon 14, and thereby you can know age of that ash bed. So you know the history of volcanic activity. Okay, so and also we try to date the crust on which the volcano is sitting, and a lot of geochemistry, isotopes, try to understand the source, depth of extraction of magma, and general petrogenetic evolution. So all these things we did, and we are still doing it. Some pictorial thing of how the lavas look. Okay, so this is typical lava flows of Barren Island. They look like that. So you can see the olivines are still there. They're eaten up, and so like a basaltic lava flow would look like. So this is what. So you get a lot of genocris, lot of phenocris, and lava. So these lavas are typical A lavas or A lava flow we call it. So yeah, so this is what I will not get into too much of it. And we did study a lot of isotopes also, and trying to figure out the source of these melts, and because it is located in a place where we should actually get a lot of crustal stuff in it, because as we know in subduction zones our magmas are heavily contaminated or have a big component from the subducting slab. But we found that Barren Island lavas are very pristine compared to its counterpart, which is called Narkundam, which is a northern volcano, which is extinct, as I told you. So they are more contaminated by the subducting plate compared to the Barren. And isotopes also tell us the same story. So overall, taking all the geochemical views, this is what we came up with, this model, that this is Barren Island, and there is a back arc here, which is emitting more asthenospheric lava, morb-like lava. So we are suspecting that this morb might be contributing to the pristine nature of Barren Island. However, this needs to be tested still. So I will not conclude it here. I will put a question mark. So this is what we are suspecting. All right. So I'll now jump to the mud volcanoes. Now, Barren Island is here. These mud volcanoes are located on the accretionary prison. So there are many mud volcanoes. There are some in Myanmar also. The big ones are in Myanmar. But we do have mud volcanoes. They are located along this highly sedimented uh, boundary, or we call it accretionary prison. So all these sediments which are piled up along the subduction zone as are actually causing this mud to come out. So if you study them, you will definitely will know what's going on below this accretionary prison. So where are they located? So if you think this is the Indian plate going under Burma plate, so don't worry about this complicated nature of the figure. So this is the accretionary prism. The actual volcanoes are here, volcanic complex, that is Barren Island, then the spreading center. But these are all the sediments. So these mud volcanoes are located along this accretionary prism, all along actually, from Andamans all the way to Myanmar. So they are heavily sedimented. The thickness of sediment could be 6 to 8 kilometers here. And that's the dicoloma, that means boundary between the slab and the converging or the overriding plate. So from somewhere here, they are actually coming through. So if you take aerial photograph, so this is the Andaman Island. So the volcanic fields are here, mud volcanic fields. So because they are mud and they when they come, they actually methane emissions will burn the forest. So you can actually they are visible from sky. So if you take a Google Earth also, they are visible there. So this is a picture from Bharatang Island, which is middle Andaman. So you see these mud volcanoes, a field of mud volcanoes. On the ground, this is how it look. Some of you might have already seen it. So not so impressive, but very peculiar. So these are mud mounds where you see this tiny mud. We call it. It has a name actually. I forgot. These are small cones where the mud is emitted, and this mud also emits these glass which are brought up from the sediments, because the Andaman accretionary prism is also made up of older sediments which are stratified and lithified. So they are mostly Eocene age and Oligocene age rocks, sedimentary rocks. So which are through which this mud volcano emits or it gets ejected. So they carry these pieces of those rocks. So you see, this is a one mud volcano field where so many cones are there. Closer looks like this. So you will have a small crater, like a real volcano. You will have small craters, and through which instead of lava, you will have what you will see. The mud is excluding. It is mainly water with a lot of gases. So gas emission will be there, and of course, these clasts will be there. So again, like the real volcanoes, here you would like to know the sources of the gas, water, mud, and how deep they are coming from, the depth of extraction, and what kind of implications they have for the 4-arc processes. Because 4-arc processes are very important in the way that whatever is subducting along the subduction zone, they do not remain same. They get changed chemically also. So, and then after that only they actually get subducted into the mantle. So that chemical change that happens within a subduction zone can only be studied through these mud volcanoes. So therefore, if you are lucky, mud volcanoes are tapping this material from deep enough for you to actually study what's going on down there. So a lot of things we did. So I'll just show you a couple of movies maybe. Uh, yeah. So a small mud vent, how it is emitting. So that's the methane gas which is emitting. So we collected this gas to study, because if you study isotopic composition of the gas emissions, water, you will be able to know the depth of extraction of these gases. So that's what we did. So these are called salsa actually. Salse they call it. So a lot of water. You can see some oily stuff is also there. So they are immature hydrocarbon also that comes. In fact, SN Bose Institute from Calcutta, they tried to monitor these emissions. So they had put this kind of collection thing, and it was connected to one GCMS. So they measured helium 3:4 ratio, thinking that whenever there is an earthquake, there will be a lot of helium emission, and that will tell us as a precursor of some earthquake. So I'm not sure whether it worked or not, but they did attempt. So they constantly collected these gases that came out. However, we had our jugad. We tried to collect, because logistically it's very difficult. So we, with some NGRI people, we did collect a lot of gases, and we studied gases, water, mud matrix, rock class, whatever came out, and tried to understand origin of these mud volcanoes. So I will not get into details. So we have published these works. So what we found that these gases that get emitted are basically thermogenic hydrocarbons. So usually you get two types of methane. One is biogenic, shallow subsurface methane or shallow surface. Anywhere, if you have biogenically produced methane, by bacteria and all that, they isotopically they will fall here. Whereas high temperature methane will fall here. In other words, the gases we saw, we actually sampled, let's say the mud volcanoes of Andaman, they sample gases which come from sources which are deep enough and produced at a higher temperature compared to biogenic gases. So that means they are actually being sampled at a very deeper depth. So we have estimated based on many different isotopic composition that this organic matter which is decomposing to produce this thermogenic methane is probably coming from more than 8 kilometers depth in the accretionary prism. So you can imagine how deep the source of these material are. Then, of course, we studied the water also. So, water composition will tell you the source of the water. So, these are isotopic composition of water. We also studied measured cation, anion, etc. I'll not get into detail, but the conclusion was this: the water which gets emitted, what I showed you, along with the gas and the mud, is actually sediment poor water. Even though it is located near sea, there is no sea water here. It's much fresher than sea water, and it is not groundwater also. So it is somewhere in between. And then we have, if you do the isotopic composition, it is very clear that they are coming from dehydration of the clays. So all these clay material, which are part of the sediment, which is subducting, undergoing immense pressure because of the subduction, is actually breaking down, and those water are getting extracted and going to the coming to the surface through these mud volcanoes. So this is what we inferred. Now the mud itself, the solid part is the mud, which is the clay mineral. So we did the clay mineralogy of those, and of course, like any other clay mineral, we studied all that is available there. And this is what typical mud clays are: smectite, illite, kaolinite, chlorite. You have some plagioclase and quartz left also, and sometimes you get calcite as well. So from different clay mineralogy also you can estimate depth of extraction. Same way, one can measure the organic matter is there. You can measure CY ratio, and thereby you can know whether this carbon or the organic matter is marine or terrestrial. And then, so mostly we found it's marine organic matter. So if it was coming from the soil, it would have been terrestrial organic matter. And we tried to date also. So the funniest thing is we found the edges here are more like soil. So you have to imagine, even though it comes from deeper depths, they are erupted onto the soil. So they will always have some kind of soil contamination. So that's why the edges are. Anyway, and then we measured in the solid part also. We measured the measure elements, trace elements, isotopes. So I will not get into all that detail. All I'm trying to say, what we found is very interesting. So these are many different isotope systematics we did: strontium, neodymium, and lead isotopes. So these are the mud volcano samples. These blue color dots you can see. So as you can see, it's basically a mixture of altered Indian marb, or we basically the slab or the oceanic crust. What is going on here? The Indian plate is subducting beneath Burma plate. So Indian plate here is mostly the oceanic plate loaded with a lot of sediments, which are derived from Ganga, Brahmaputra, or Irrawaddy. So those sediments are will be calling trench sediments, whereas the altered oceanic crust is your slab, or the oceanic crust, which is altered, of course, that's old. Now, this exactly doesn't, we would think that all these mud should come from trench sediments. But what we see that a lot of these mud clays are actually derived from the oceanic crust itself. So this also tells us that actually the mud derivation is happening at the boundary between the two plates, which we call decolonna. So if that is so, then how does the picture look like? So this is, we just published this year only in chemical geology. So this is what our model is. Of course, it can be questioned. So we suspect we have a, so you have to imagine this. This is the subducting plate, and that's the overriding plate, all of it. Here is the accretionary prism where all sediment is deposited. and the trench is somewhere here. So this is the decoloma, where the subduction boundary, you can say. These subducting sediments are actually piling up below the accretionary prism. So the accretionary prism is already very old, and they are from, you have Cretaceous ophiolites and then Eocene sediment and Oligocene sediments also. So they are all rocks. Below that you have soft sediments which are being thrust into or pushed into the mantle, but it is not able to go. So they are piling up. They are forming some kind of melange. In fact, some of these melange, old melanges, are exposed on the island. If people have done field work, they would notice such melanges. And here only all this gas, water, everything is getting generated, and they are getting ejected through the fractures or faults, because accretionary prism is full of this kind of reverse faults. So along which they can get emitted, and you form these mud volcanoes, which carry material from the interface. So if you, by studying this, we are able to find how much is actually going into the mantle. So surprisingly, because of the very nature of subduction here, very little of subducting sediments actually go into the mantle along Andaman subduction zone. So that's very unique. That's what we inferred. So now I will summarize this. So whatever I discussed, two contrasting type of volcanoes. One is really volcano, and the other one is a look-alike. But both are important for our kind of study. If you are trying to understand subduction zones and the processes within it, both are very useful. The first one, the Barren Island, is the lone active volcano of India, and it provides valuable information about the complex mantle dynamics beneath the current Andaman volcanic arc. And it has been active since at least 1.8 million years. In fact, we have a lot of ages which I didn't show. Whereas the mud volcanoes, which are located along the Andaman Islands themselves, in the sense in the accretionary prism, they provide valuable information about the four arc processes. So it is before the arc, real arc, what's going on, and they will give you some idea about the alteration processes sediments undergo and the crust also undergo before actually being subducted. So I'll leave it with that, and thank you very much. So on the left, the real volcano, on the right, the mud volcano. Thank you very much.
Thank you, sir, for the wonderful talk. Now, I invite the questions from the students. Yeah. Any query, questions? Yeah. No.
Thank you, sir, for this wonderful presentation. My question is, can the mud volcano be a faithful indicator of hydrocarbon deposition?
Can the mud volcano?
Be a faithful indicator of hydrocarbon deposition?
Sorry, I'm not able to hear. Can somebody please?
Sir, I must say that can the mud volcano be a faithful indicator of hydrocarbon deposition? Can I rely on it? यहाँ mud volcano है तो hydrocarbon deposit मिल सकता है.
Sir, he is asking that whether the mud volcano can be indicators.
Not audible, sir.
Hello, sir. Sir, is it audible, sir?
Now it is audible.
Sir, he is asking that can this one minute? Sir, can this mud volcano an indicator of the hydrocarbon deposits? He was asking like this.
Petroleum deposits.
Hydrocarbon.
Yeah, definitely, yes. That's what I was telling. They are indeed. In fact, ONGC has explored a lot of these mud volcanoes which are offshore, and they are indicators. The thing is, only they are not, the maturity level won't be there for extraction. But I'm pretty sure they are the indicators of where these actually hydrocarbon deposits are being generated, because all along these Andaman Islands, on the Andaman Sea side, there are a lot of mud volcanoes under the sea. I mean, it is on the sea bottom, so they give some indication about where the petroleum deposits are. Yes, they indeed tell us, because if you measure the hydrocarbon emissions coming out of this mud volcano, you will know actually the where is the source. So it is possible. Yes, people do use it. It's not unknown.
Thank you, sir.
Yeah.
Next question.
Hello. So, sir, my name is Abhiraj Bharatang, and I am from MSc second year. Sir, my question is, sir, is there any specific use of this volcanic mud? Like, can you use this mud in some kind of economically or some other uses of this volcanic mud?
Specific use for what?
That is volcanic mud that is coming.
Yeah.
Is there any specific use for that?
Use for what? Societal application?
Yes, sir. Any kind of application like.
Well, well, volcanoes are known to, particularly if you know Iceland. In Iceland, all these volcanoes, they have a lot of volcanoes, first of all. And volcanoes, if you have the water that gets, suppose you have groundwater there or sea water, they will become high temperature geysers kind of thing. So geothermal energy is something that people extract if you are close to the volcanoes, and it's a very common practice in Iceland, where geothermal energy constitutes probably 30-40% of their energy. So, but in India, first of all, geothermal energy is still not. I mean, it's not been, what do you say, put into use, and Barren Island is too far. Even though it has a lot of energy, extracting that energy and giving it to, supplying it to people would be difficult. So therefore it's not something that is useful. And this volcano is a small volcano. So in Indonesia, most of the volcanoes are rich in a lot of deposits, mineral deposits, particularly sulfur. Active volcanoes are rich in sulfur. In Barren Island also, if people have GSI people have gone and to the top, you do see a lot of sulfur deposits. But I don't know whether it's worth extracting that sulfur. It may not be a big source. Yes, I mean, volcanoes do provide a lot of material for society, but our volcano is very far away to, to actually help us directly in any way, other than for scientific applications, to understand what volcanoes can do, what information they carry. So for studying them, it is a good example where people should go and study these rocks. Other than that, probably it has no other application as of now. Maybe it's a good tourist spot. Yeah, it can bring in some money for the government.
Uh, there is one more question, sir.
Yeah, yes, yes.
Sir, I would like to know how OSL dating is useful to determine the age of volcano.
So you have to repeat that question for me, somebody, please.
How OSL dating is useful to determine the age of volcano.
Sorry, how?
How OSL dating is useful for determining the age of volcanoes.
Age of what?
Volcanoes.
Volcano.
Volcanism. Age of volcanism. OSL
Uh-huh.
for volcanism.
I'm
So how OSL dating is
OSL date.
yes sir.
Okay. Oh, well, we tried, it didn't work, but there is one paper though, I'll tell you. On the volcano itself, there are a lot of ash beds. Okay. So, if you want to date, first of all, these are very young rocks because we now the date things I didn't show you entirely, but the volcano we have dated to be 1.6 million years old. That means the bottommost lava flow is 1.6 million years old. That is dated by argon method. It was dated in IIT Bombay. So the older rocks which are present below sea level were not accessible. However, you get genocrysts. In younger lava flows, you get older crystals which can be dated. So from there, we found the crust on which the volcano is sitting is 100 million years old. Okay, and there are lava flows which are 3.5 million years old also. That means those lavas are older minerals have been picked up, magma chamber rocks have been picked up by younger lava flows, so you can date it. Now if you want to date younger things after that, 1.6 million year, it is difficult to do any radiometric method. So OSL is something we attempted. So there are ash beds. I showed you the eruption taking place, they get deposited. So from those ash beds, like a sand body, you can take a sample and try to study the luminescence, OSL. So the issue is with these ash beds is that we don't have enough quartz. Probably there is none because this is a basaltic volcano. Now basalt, as geologists should know, don't have quartz. OSL works best when you have quartz. But however, this has plagioclase, and there is also no potash feldspar. So plagioclase, there is a colleague of mine in PRL did attempt. In fact, he has a paper in quaternary geochronology. So he predicted, before we actually did this dating, he predicted it could be 1.5 million years, and argon gave us 1.6. So it is a possibility. People are exploring whether plagioclase can be dated by OSL. So far, I have not seen any strong, paper, they are successful paper. But let's hope in future we should be able to date these minerals. So then we can have a history. But what we did, instead of dating, which is exposed on the surface, we went to the sea because this is beautifully located within a ocean basin. All that ash gets deposited in the sea, so you can take a sediment core. So we took sediment core, and we in fact we have couple of papers actually where we have showed the activity from 60,000 years ago to recent. So there have been many major activities of this volcano, which erupts, ash which gets deposited. So you can date the sediment by carbon 14. You don't need to date the ash. You date what is on the top, what is on the bottom, or you can even get foraminifera within the ash bed. So when ash gets deposited in the sea, from that when it goes down, it carries along with all dead animals, and then those animals, organic matter, inorganic matter, you can date. So that's how we built up the eruption history of the volcano. So otherwise, OSL has limited application in basaltic volcanoes.
Thank you, sir. Is there any questions from those who joined online? If anyone will ask a question. Since there's no question, so sir, we would like to thank you for the excellent talk. It was a really a new talk, new experience for all of us because the talk itself is very new. For myself, also got to learn so many things, especially on one, what's the volcanic activities and subduction process going on. So you are the person that can actually bring the information from those remote places and then share with us. So thank you so much for that, and also thank you for your time and your presence. Thank you once again, sir.
Thank you very much for inviting me, and it was a pleasure. Thank you.
Sir, we would like to felicitate you with a token of our love. So please, through online.
We'll send it by post.
And then it is going to be sent by post to you.
Sure, sure. Oh, that looks big. I can. He showed me here in the camera. Thank you. Thank you, Jitendra.
All side, like one side.
No, it is not visible there. Jitendra, on the back. Ah, yeah, this way, yeah.
Yeah. This is Jai Vigyan,
Jai Vigyan, okay.
Jai Kisan,
Uh-huh.
Jai Jawan and
Jai Jawan, Jai Anusandhan.
Anusandhan, beautiful. Thank you.
Thank you so much.
Thank you very much,
Post
sir.
it to
Milan. Thank you.
So we'll have another talk, and it's going to be the last talk of the event. So for this, may I request Dr. Suparna Tiwari to introduce today's guest, Professor Satish Sangode, sir.
Thank you, KK sir, for giving me an opportunity to introduce our guest, Professor S.J. Sangode. He is present with us in the occasion of our Day celebration. So, Professor Sangode is the professor of Savitribai Phule, Pune University, and before joining there, he was a scientist of Wadia Institute of Himalayan Geology. He is basically working on paleomagnetism and environmental magnetism, and he's the recipient of DST Boycott Fellowship as well as Liverpool University Fellowship for postdoctoral in UK, and he has published more than 116 papers in different national and international journals on climate change and sustainability. So, sir, I would like to request you to come here and share your thoughts. Over to you.
Thank you very much. I'm thankful to and thankful to Honorable Vice Chancellor for inviting me. And I'm enjoying the Earth Day here with all the faculty, students, and everyone. So, somewhat a different topic, but this is really a work on my book that I'm working for last 6 months on this topic. So I would like to share some of the thoughts on this topic. The sustainability advances the earth science, rather earth education. By education, that also I would like to explain that one. And the talk is divided into some three topics: an overview and meaning of the sustainability, the global awareness and actions, and the Indian scenario, earth education and inputs to national education policy. So if you look at the earth in a different perspective rather than a routine visualization, if you look at it, it comprises about 98% inorganic matter and about 2% organic matter. These figures are very broad. And the organic matter we can then divide into non-living and living. The living human species, they comprises less than 7.7%. And human also represent one of the latest arrival in the geological time scale amongst thousands of other species. A very common knowledge, but I need to specify. And we should see the efforts that Earth took in building the life and also the life supporting inorganic ecology. So if you look at the early Earth perspectives, we can divide it by geological time scale. The early Earth we call Adian Eon, and Adian era, and then Archean and Protozoan. So the earlier the was totally inhospitable. The Adian time was inhospitable. The crustal temperatures were very high. We can say surface temperatures were more than 100 degrees. So it was totally inhospitable. But in this inhospitability, it started preparing an inorganic ecology in the form of minerals, in the form of water molecules, in the form of some gases which are later on reacted to form more favorable gases, atmospheric gases. And then follows the Archean. The Archean time, we started getting oceans. Still, these oceans were not hospitable. But we started getting the photosynthesis, earliest photosynthesis. And during Proterozoic, then it was quite favorable, producing the oceans, producing the oxygenated ocean and as well as atmosphere, increasing the oxygen levels. All these conditions were quite favorable for life, for organic buildup. And the efforts of so many, about 80% of the time of the earth, that resulted in the biological activity, organic matter, the organic compounds. By about 500 million years, we started getting a good buildup of the living matter. But before that, whatever the earth has done, we probably know very little about it. Probably a lot of biochemical reactions, biomolecular reactions, biogeochemical reactions at each and every place on the earth. Countless reactions, countless experiments by the earth that resulted into build-up of these compounds, like the development of the prokaryotes, then eukaryotes, then multicellular organisms, and then animals, plants, and whatever we are seeing. So it is impossible to count, even to understand, and even to replicate those reactions that were carried out by Earth for so many million years. And the latter part also, we can look at the different biomolecular reactions, where the inorganic ecology, inorganic substrate, the minerals, ions, all were very important. Including first and most important component is water. And then for long time single cell life forms. Then photosynthesis resulted into vegetation, algae, and all other different kind of life forms. Then eukaryotes, where sexual reproduction started in different kind of life forms. Then multicellular life forms, and then entirely the Cambrian explosion, where the life was exploded. Number of species, number of different species were reared by the earth. So this was some kind of rendition of the Eden earth. It was very difficult to survive, but it provided the inorganic ecology, as I said. In the Eden time, the water molecules could have escaped from minerals, from deeper part of the earth. Water molecules, hydrogen, helium, they escape. And lot of helium that is escaped, being very lighter. Lot of hydrogen also escaped. And that gave rise to the better period of Archean, when oceans were formed, but still these oceans were not hospitable. So if you look at the entire progeny or the entire methodology that was adopted by the Earth, so many experiments, we cannot understand with the present day knowledge of the science. Now, present day, you must have heard the organic compounds, the lives are being created in laboratory, but those are very primitive, and those life forms available from the knowledge of paleontology, and those life forms they did not preserve. They are infinite. There are many different kind of experiments that resulted into the evolution of life in integration with the evolution of the atmosphere. So this is just to impress that the efforts of the earth, and we cannot, even I am not expert to explain all this early life, its interaction, inorganic, organic interaction and reactions, and the evolution. What is very basic to us is the thought or the need that oxygen, water and food, these are the three basic elements for metabolic survival. And fetching these elements without harming the earth is the art of sustainable living, the meaning of sustainability. There are different definitions of sustainability given by different organizations, including United Nations. But in a very simplistic manner, what I understand, this is the meaning of sustainability, which is rightly adopted by all other species except humans. All other species are readily sustainable. And the knowledge as to how these basic elements are maintained by the earth is also inherent to everyone. However, humans have focused on all other knowledges and technologies except the sustainable earth. And the efforts of sustainable living does not need a rocket science, but it begins with the science and art of observation of the fundamental knowledge about the earth. And further, the remedial measures, they definitely need a very advanced science that cannot be replicated in the laboratory. Probably our science is not yet evolved to provide the remedial measures what the humans have damaged to soil, to atmosphere, to ocean, and all other living and non-living species except human, including human also. The damage controls and the reversals definitely need great wisdom and advanced technology founded on the knowledge about the earth. So these two parts, if you really want to see from the perspective of the education policy or inputs to the education policy, the first kind of knowledge, fundamental knowledge, which I said based on observation, but not necessarily based on observation, we are having much more details. That is essentially a primary or secondary level education, like geography. Geography, we are not classifying, we are not separating from the education. Geography is very much included, it is built up in our education system. So why not the earth science? Why this kind of knowledge should not be included in the earth science in the school education as essential part and not a specialization. And the specialization can be inducted for the second point, that is the remedial measures, preventing the damages, and many other advanced topics that should be the at the level of higher education. Now, we are in a situation where we have a lot of awareness, but little knowledge, and the actions are not really based on those knowledge. The actions are based on the awareness. To give an example, today morning we have seen majority of these school students, they were very aware for saving the environment, pollution, save water, all these things. Even school children, they talk very nicely, they have the idea to save water, and that is awareness. On the other hand, that is just an awareness, but that is not a knowledge. For example, in a city of Batinda, what are the surface and groundwater interactions? What are the evaporation, precipitation components? How the groundwater interacts and how humans are influencing the groundwater? Probably you need a PhD. So PhD researcher, he does in detail 3 years or 4 years and produce the knowledge. This knowledge, the PhD scholar or PhD holder may not have awareness or may not be serious about the awareness, because his thesis may go into library and it will be kept in the shell. So there is a gap. A gap is created between the awareness and knowledge. This gap has to be reduced. What does it mean? It is not necessary for even the school student to know about the hydrological or hydrogeological information. He is well aware. On the other hand, the PhD scholar, he need not to know about he need not be aware about this, because after getting PhD, he will get some job and he will go somewhere. But the thesis remains there in the library of, say, Central than sustainable living. Example, if we have some biological problems because of the, say, climate change or some water pollution or something like that, we immediately go for remedies. And that is also not a sustainable living. Instead of treating the pollution, we are treating ourselves. That is not a sustainable solution. And we need to think more and again whether all our actions and policies are based simply on awareness and not the knowledge. And at this stage, then we have to review the status of knowledge available to us, especially for earth science. I am speaking entirely for earth science. Probably if we are talking about information technology, database and data science and all these things, probably that is not comparable. We don't have the status of the knowledge, the useful knowledge. Neither our textbooks in geology or many other earth sciences, they teach us how to produce or present the knowledge in the form of data. Our knowledge is largely observational. So do we have sufficient knowledge about the earth? That is the prime thing. And whatever the status of knowledge is there, whether we need to have this status of knowledge at secondary education level instead of the higher education. And as I said, that the earth science is a fundamental knowledge. It is not a specialized branch of science stream or faculty. And if we call earth science as earth science, recently only we started talking last 10 years. Otherwise we used to say geology, geoscience. Then we started talking about the earth system science. So this restricts the common graduates from learning about the earth. Why common graduates? From engineering, technology, medical science, why they need the knowledge of sustainability? That also we will see. Why an engineer should produce sustainable products. Why an architect should produce sustainable architecture. So everyone needs, including medical science, everyone needs the knowledge or the inputs from sustainability. And to large extent, this sustainability is related to the knowledge about the earth. Not necessarily earth science, but knowledge about the earth. Then many people will argue that already there is one subject, geography, that includes the knowledge about the information about the earth. Then do we need separate subject for earth education and sustainability? So I will try to convince from both sides. And probably I will try to emphasize at what level, what kind of earth science, earth education or earth knowledge should be there. Say at primary level, secondary level, high school level, intermediate level, at higher education, science and technology. Then we always talk about the sustainable future of the earth, which is just an ego, a human ego, to talk about the future of the earth. Rather, more correctly, he needs to think about the future of human species on the earth. Earth itself is self-sufficient. It is cultivating its own future. We need not to think about the future of the earth. For millions of years, the earth has managed the future of its own. And probably introduction of human is the biggest mistake for earth. If you look at all the effects created by human, to what extent we have damaged the earth, what human interference are the other living entities of the earth, and how can we parameterize these misdeeds? Because if you are in the law of nature, natural law or law of code of nature, then you have to count what are the crimes created, what are the crimes made by human. And in order to know these crimes, then we have to understand. We have to parameterize because law is universal. So one person killing someone in Punjab will get same punishment. Someone killing someone in Tamil Nadu. So there should be universalization of the knowledge about the earth. Not only the knowledge about the damages caused made by human on earth, and the remedial measures that can revert at least some of these damages. We need better knowledge about the earth. Humans have damaged the earth to extreme conditions. Extreme, too much extreme we cannot imagine. Even the natural processes did not damage this kind of extremities. The example through wars, weapons, and the destruction of soils. This destruction by metals and other weaponry in the soil remains there for thousands of years. Soil is damaged through excessive hydrocarbon usage. Earth might not have never thought that human will explore for hydrocarbon, exploit the hydrocarbon, and it will damage the interior as well as the exterior of the earth. Through mining, infrastructure development, so billions of crimes. And in the code of nature, which never got the place in books and our education system. So our education system needs to introduce this knowledge. This is not simply science. Knowledge is above science. So this knowledge has to be introduced. Then if you look at that scenario, then we have to modify the definition for sustainability. And add sustainable action and sustainable development. Because ultimately, development, growth, these are the foundations for every nation to grow or to progress. One, to identify the crimes violating the laws of nature. Second, to repair the damage to maximum possible human capacity. And third, to adopt the sustainable living practices. To follow these three principles, we need composite knowledge of the earth science. And from morning, everyone is saying earth. Very proudly we say the mother earth. Then why not the science of the earth is the mother of all sciences? Then why we need to separate out earth science or geoscience or geology as a separate branch? Definitely it needs separate branch at higher education level, but why not it is a fundamental science? Then recently, last 10 years, lot of more than 10 years, but last 10 years I will just benchmark lot of awareness about the sustainability. Before that, climate change, environment, everything was there. But since last 10 years, we started talking, rather globally, people started talking about the sustainability. Sustainability of the future Earth, which also compels us to know more and more about the Earth as generalists as well as specialists. And the Earth education and our Earth IQ needs to be enhanced. This is where the national education policy is a constitution for Earth education. It is the only way to adopt the sustainability, to understand the sustainability, and also take the actions for sustainability. It is a tool for transformation of minds and practices towards sustainable living as the law of nature and the future human existence. The national education policy in India, sometimes we call new education policy, but after 5 years this will also become old education policy. So if you look at the evolution of the national education policy, it evolved in benchmarks, separated by 5 to 10 years. So probably that time it was all right, but looking at the present day dynamic changes, like climate change, disaster, dynamic changes in socio-economic aspects, socio-economic thinking, you will see these benchmarks are widely separated. And the need for frequent revision is necessary, rather an intelligent policy should be formed so that it is quite flexible to adopt the sustainability at all levels, elementary, primary, secondary, higher education. And whether the policy makers, what is the foundation the policy makers follow to develop any such policy, whatever may be there, but they should understand the current generation and future generation. Policymakers are old people, more than 50 years, 50 plus or more than that, very experienced people. And they represent more and more generation gap. Even today's parent cannot understand what their son or what their kids are thinking. There is a generation gap. So that generation gap is another danger for devising the poor policies. And then all these policies, at least the current, all the future policies, has to integrate sustainability, education and development. Because if we don't include development, then the growth of nation, and no leader will agree. No one will agree unless we talk about the development. And if we have good education on sustainability, on earth science, but development is not following the sustainability, that is also dangerous. To that end, I would like to show a very futuristic depiction that is called Hubert's curve, who depicted how the development progress is harmful. It leads to more destruction by giving the examples, real examples, and also by prediction. And many of these predictions became true. So this curve, again, more detailed curves are there. But this is an interpreted curve. Is really based on the energy sources. Hydrocarbon production, industrialization is linked to the hydrocarbon production, more energy sources, more prosperity, then destruction, probably war, probably conflicts within the nation, between the nations. All these are recorded and you can see the depiction. So it will be difficult to understand what philosophy behind these events. For me, not being a philosophy student. But at least we can understand the Hubert's peak in current scenario of unsustainable growth. There is a direct relation of natural resources and energy resources to industrialization, employment. You will get more employment, more prosperity. That will result more population surge, more urbanization, more unsustainable living, further leading to extra pressure on the natural resources. Whenever all over India we are in an age of infrastructure development, and proudly all the leaders they say infrastructure development. We are doing this infrastructure development. Where from this infrastructure comes? From nature only. Natural resources. Cement comes from limestone. Metals, iron ore, aluminium ore, and many other metals, copper and many others. There is excessive demand for all these natural resources. Side by side, infrastructure development also demands energy, transportation, petroleum product, hydrocarbons, everything is increasing, and that yields higher cost of all the commodities increases, and that is rightly depicted in the Hubert's peaks and drops. Drops are destruction, wars, famine, or many other problems. Hubert's peak also tells the impact of wrong applications of the sustainable growth. Example, the excessive use of alternative energy resources at wrong points. Today, I think we are exactly at that wrong point, such as at the helm of industrial growth based on conventional energy sources. Our technology is not sustainable, but we are introducing sustainability. Example, the introduction of the electric vehicles. If you buy electric vehicle, probably our habitats are not supporting the electric vehicles. If I want to buy electric vehicle and go somewhere outstation, I may not get a charging station. If electric vehicle is faulted, it fails, I don't get the mechanic. That means technology is not available by the time we introduce the electric vehicle. Just small, may not be a very good example. Then without adoption of the sustainable living practices. As I said that here we are talking in the air conditioned format, this is not the sustainable living. We are talking about something sustainability, but we are not adopting the sustainability. Then the understanding the current generation as well as the future generation. Understanding the human evolution means what are the cognitive capacities at different age levels. and whether these cognitive capacities are changing from generation to generation, and what is the relation of information and the cognitive capacities. All these are to be understood in a human psychology, has to be understood before introducing the earth education into different levels of foundation, preparatory, middle stage or secondary stage. I am not criticizing the new education policy, I am just generalizing. These are the inputs to be given to the new education policy. The new education policy or national education policy is in fact a framework. In this framework, we have to introduce our subjects, our syllabus into that framework, so the responsibility remains with the educators or teachers and not with the policymakers. And also, to large extent, we have related our education to career. So, there is another problem. How we are relating education to career? The example is more and more skill development courses. More and more skills are necessary. And we are subduing the knowledge. Skill is different, knowledge is different. With knowledge also you can develop the skill. It doesn't mean knowledge, if you have knowledge, if you don't have skill. With knowledge also you can develop the skills. Then the disparity between the demand and supply that results in unemployment. I have not again talked about the entrepreneurship and other factors, but simply unemployment. That is also the fault of the current education policy system. And the dynamically evolving technology and blind adoption of the market driven by technology, Western driven market technology, changing needs of application, service, evolving social fabrics under equally dynamic global scenario that demands every stream of education to concern the new framework. Vision is often founded based on goals, and goals are founded based on vision. And if the goals are uncommon, it results into conflict. The goals may become common and normalized when the target is singular and when the target is survival. If we are talking about the human survival, another 5 years, 10 years or 20 years, then target should be singular, the survival. For example, the goals become common during wars in a nation, during disasters. And the common goals can be decided by the nations, but the most common globally accepted goal should be sustainable living. The sustainable living practices. Whether it is really common, whether globally it is, people are thinking that this is a common goal, that can be evident from the United Nations framework for sustainable development goals. United Nations formatted some 17 goals. So if we don't have any other thing, then can we think about these global goals, United Nations global goals? That also we will see. Then what happens? The common beginning of education at elementary level later grows into specializations. That is, it grows into heterogeneity at the degree level or higher education level. Then later on, at this higher education level, we talk about the interdisciplinary science, integration, interdisciplinary, or merging various applications from different science. Now this is, we are in that age, interdisciplinary. That results in artificial homogenization of the goods. What I want to say, the knowledge about sustainability and earth science or earth should be continued from the elementary level and not at the latter level. That will create a weak kind of development, sustainable development. So it is necessary for us to decide the long-term goal of education with common aim as sustainable practices. The education policy provides a framework, the structural framework and pedagogy. And second part is designing the contents and its delivery. So it is the job of educators, syllabus designers, to understand the meaning of sustainability and to introduce into the curriculum. Then every specialized branch is biased to justify their own significance, even in absence of code. But the sustainability allows such justification, maintaining the common goal for all the branches, anything including science, technology, social science and humanity. So a nation needs to define the sustainable goal, and these are fortunately readily available from United Nations Sustainable Development Goals, which are global, which are universal, taking into account of underdeveloped, developing and developed countries. Rather, they are more focused for underdeveloped and developing countries. I will skip many of these things to have some overview about the sustainable goals. So I will not overview because this will take a lot of time. I have to abruptly stop somewhere because of time restriction. Not only because of time restriction, because my book is incomplete. If I complete my book, probably I can conclude. So I will stop somewhere abruptly, but let us see some examples of these goals. So I am not here to promote the United Nations Sustainable Goals, but let us see the meaning. We all need to understand the meaning of these sustainable goals. That can be taken as reference, and every goal can be evaluated. First goal is end poverty in all its forms everywhere. How it is linked with the sustainability. You cannot expect a poor man who is surviving for his daily wages to adopt a sustainable living, neither by knowledge nor by compulsion. So poverty is the major hurdle developing the sustainability. Major hurdle in developing the sustainability. Poverty is very complex, multidimensional problem, and countries with large population they are classified into lower class, middle class, and upper class. Forget about the upper class, but by population, lower class and middle class. And in fact, there is a good permeability between lower and upper class. The lower class population is transferring to the middle class. You cannot put a dividing line. Poverty is not permanency. Poverty is that critical below poverty line, so it is not permanency. It is a highly flexible, highly fluid kind of phenomenon. So, in this scenario, what sustainability can do to remove the poverty, and whether directly removing the poverty we are going to adopt sustainability? No. Simply removing the poverty, we are not going to adopt the sustainability. We need to adopt the sustainable living practices. Those practices should be adoptable by this poor class, below poverty line, so that automatically this lower class or below poverty line can go ahead. So that is just one example. As I said that we don't have time to discuss all these 17 goals, but every goal can be discussed to our indigenous conditions, to develop the indigenous policies, adopting these United Nations Sustainable Development Goals. So all these goals, they contain a knowledge about the earth science, a knowledge about the earth, including the poverty. I am not describing in detail. That also you need for sustainable living, you need knowledge about the earth. End hunger, achieve good, this is second goal. Ensure healthy lives and promote well-being for all. Ensure this, in fact, I have described how sustainability is related in an Indian context. In my book, I have tried to describe all these goals in Indian context and where is the input from earth science. So I will just go ahead with this. And some of the goals are really earth science only. For example, climate change. It is totally earth science. Climate change, if it is a common goal for United Nations, means climate change is a common science. Climate change is part of earth science, so it is a common science. It is not a specialization. Conserve the sustainable use of oceans, seas, and marine resources. Now, everyone, including many, there is, I think, international ocean year or something is there, and blue economy and all these things are now at the priority for many nations, including our Indian Ministry of Earth Science. They are focusing on blue economy. So what is that blue economy? I tried to elaborate. I am not advertising my book, but I tried to elaborate, and we don't have time to elaborate. Blue economy is designed, but whether it is sustainable, that is a question. We have a lot of ocean resources, but are we going to exploit them sustainably? That is very important. Protect, restore, promote sustainable use of terrestrial ecosystem, sustainably manage forest. All this, what is this? This is all earth science. Promote peaceful and inclusive societies for sustainable development. Provide justice to build effective, accountable institutions. All these are the lot of inputs. They need lot of inputs from the earth education, knowledge about the earth and earth science. So what we need is the intelligent leadership, learned leadership. How can we develop learned leadership unless we infuse the knowledge about the earth into our education system? That means we need another 5 or 10 years to develop this leadership, to develop the visionaries, to develop the system and framework. Extreme advancement in technology has to be stopped. All the advancement in technology, most of these technologies are not sustainable. But we need advancement in sustainable technology. We need a lot of restrictions, laws, green jobs, sustainability consultant, legal advisors, and to introduce sustainability into legal system. That is very essential. Then only we are very notorious. Unless it is a law, we don't adopt. So all these things I will stop here, and I try to impress why and how the knowledge about the earth is a fundamental knowledge. It is not science, it is not technology, it is a fundamental science to be understood by everyone, and the advanced knowledge is a specialization. And here I want to stop this. Thank you very much.
Hello, sir. So we are students of Masters of Geology, first year. Before we proceed with our efforts of achieving sustainability goals, I would like to hear from you that many world organizations and governments are offering numerous sustainable solutions. For example, United Nations Sustainable Development Goals. So, based on all those efforts and human progress through the course of time, is it really true that the more humanity progresses, the more we go away from sustainability?
Yeah, that is what is. I gave the example of Hubert Speak. So, Hubert Speak that tells that progress is detrimental. In fact, that is not a good practice. But sustainable progress, if you are doing, I think that is more adoptable, much better, and more. It has more light.
Thanks, sir.
Thank you, sir.
Any query from online? No query. Thank you so much, sir, for the wonderful talk. Sir talk was actually based on the sustainability of Earth. Sir has talked about the mechanisms, the solutions to arrive at how to, have a sustainable environment through education, through, policy making, and so on. So thank you so much, sir, for the wonderful talk. And may I request our dean of the school?
I want to say something.
Yeah, please.
Okay. Thank you, Professor San. First of all, I am thankful to you before you traveled a long and you just agreed on our single request. So I think we are proud to have you here, and thank you very much for enlightening our students about sustainable development goals. Here I also like to inform you that we are also working on the sustainable development goals, and 3 of the sustainable development goals, climate change, energy and water conservation resources, for the state of Punjab has been done by our department. So all these 3 chapters has been submitted to the UNDP and they have already accepted all these 3 for us. So our faculty is also doing a lot in this field, and we listened to you and we also came across some new ideas from your presentation, and that is a great for our students. So thank you very much, sir, for enlightening us. Take care, sir.
Thank you so much, sir, for sharing your experience and knowledge. Now, may I request Dean to finish today's guest?
All the faculty, please come. Please, sir.
Now it's a tea break. So tea will be served at the reception area, and we will be proceed with the poster presentation by the students of our departments, and then followed by prize distribution and closing of our ceremony. The poster presentation is from all the departments of the school.
कितने बजे रीअसेंबल हो गए बोले 5:50 अभी टी है ना हाँ अभी टी है रीअसेंबल at 5:50
So we all will be get together here back at 5:15 without fail, because there is a prize distribution and we have to close the session. Okay.
इसका अभी तो इसका ये हो गया ना